All right, good morning. This actually has one title. It's going to be two separate presentations, so it's not directly related. The Mare Nostrum5 update and the OpenMP offloading efforts for the DPUs. So I'm going to start with the Mare Nostrum5 update. And first, a disclaimer, I'm not from the operations department, so I'm a scientist, a researcher. We couldn't find anyone from the operations department that could give this talk coming on this date, so I'll do my best. I may not be able to address all of your questions here, but let me give it a try. So this is actually a picture of the chapel. If you have ever been in BSc premises visiting the Mare Nostrum 4 on previous Mare Nostrums, this is what it is. The current under production system within the chapel. Now we've had to enable a different space, much larger, but I will explain in the coming slides. So the slides are by the operations manager, Sergio Girona, the operations director. This is what we have now, the Nostrum 4, as I mentioned in the chapel, with 11 petaflops on the general purpose cluster, and then 3 CTE partitions, which are for emerging technologies, to test emerging technologies at that time of deployment, of course. So we have one with Power9 and Volta, another one with ARM, and another one with AMD, which resemble to the respective supercomputers that were to come at that time. So in the bottom, you see some story of the first Mare Nostrums, very briefly, from Mare Nostrum 1 in 2004 to Mare Nostrum 4. So you see also we went from 42 teraflops to 11 petaflops in the latest that we have in production. And so you also see the rankings that we have been in Europe and in the world. We have had recently a shift in our aims. We do not aim at being the top in the top 500 or among the top 10 or whatever, but rather to be able to achieve a larger efficiency in many of the applications that our users are running these days. So we start with this PRAISE infrastructure in Europe. We are one of the 5 hosting members. Overall, we offer 220 petaflops of peak performance on 7 system, and this is like you apply if you belong to PRAISE, and you get over a peer review, you get or not get the core hours. But now we are switching, or we're joining this Euro-HPC joint undertaking initiative with all these countries that you see here, which is building a set of European infrastructure. So it's a legal and funding structure, as most of you will probably know. So it will also support this research and innovation program to develop hardware and software techniques and technologies for these new supercomputers. So now starting to come to Mare Nostrum 5. This is a pre-exascale supercomputer, as it was granted. So it's a consortium of Spain, Portugal, Turkey, and Croatia. Very separate geographically, but this is what we have. Spain will be the hosting. So we in BSc premises will host the Mare Nostrum 5 machine. We're actually already building it, and also I'll show pictures in just a few slides. So it's going to have 200 petaflops of peak performance, and it's supposed to be an experimental platform to create supercomputing technologies made in Europe. This is what we promised in the procurement, or in this proposal for the funding. So the total cost of ownership is 217 million euros. This is the big picture of the concept of a machine. So you have the public services with the login nodes, virtual machines, cloud services, and external data transfers. And perhaps the most interesting for me is this compute partition. So a few of them are planned. The biggest is the general purpose partition. There's a smaller partition with accelerators, DPUs, and also some emerging technologies that I will explain a little bit next. So there's two main networks for management and HPC. There's Ethernet and InfiniBand, and also we have the storage and the administrative services. So this is a picture of the main site of Mare Nostrum5. I will show also some numbers and further pictures later. So basically, you can see over there, there's some visiting, there's an aisle where you can go and see the actual machine, actually how we're building it right now. We schedule visits, actually. So this is what was scheduled for March 23. I believe it's not fully finished, but we're about it. So it's not that we expect a lot of delay here. We have the InfiniBand NDR200 with FAT3 and all the storage, and this is it. We actually they were calling for volunteers recently to help installing the tapes, the disks. So these two are coming next, April and June, the general purpose partition with the Sapphire Rapids from Intel, with a peak performance of 45 petaflops and sustained HPL of 35. And the accelerated right next with Sapphire Rapids again, but this time the accelerator will be an NVIDIA Hopper with 260 petaflops and sustained HPL of 163. After that, there will be this to finish the next generation general purpose on your left. GPP is general purpose with NVIDIA Grace. These are smaller partitions to just test upcoming technologies. 2.8 petaflops and sustained SPL of 2. And the next generation of accelerated with Intel Emerald Rapids and Intel Rialto Bridge, with 6 petaflops of peak performance and sustained SPL of 4 petaflops by the end of the year. So I've selected a few things that I would hope are interesting for this audience. First is the HPC network. So we will have, mainly I would say for the sake of the money, most likely, it's not a fully connected. So it's a full FAT3 on the islands. So we have several islands in both the general purpose and the accelerator, and also for the I/O. And so those islands, the SLARM workload manager is aware of them, so it tries to schedule them, the jobs within the islands, and then it's not fully connected to the outermost or the higher level switches. You can see here the contention rates on the general purpose and on the accelerator. Right. So basically, we can just wire everything, of course. Also, this is an interesting, full of data slide. It was the most interesting for me when I watched these slides. So you see here all the partitions, all the different processes that we have, different memories. So let me highlight some. Maybe I can use, maybe it's not a good idea. Let's try to do this. So on the general purpose, the main one, we have 90 racks, and the biggest partition is 6K cores with 2 Sapphire Rapids processors per node. And it has 2 different flavors. The largest will be with 256 gigabytes of DDR, but there will be a few nodes, 216, with 1 terabyte of memory. And this will be 35.4 petaflops in HPL. So we'll have 1 rack with 72 nodes, with 2 Sapphire Rapids, and with HBM. Right, it's here with 0.5 gigabytes of HBM per core, 128 gigabytes, and 32 gigabytes of DDR5. So on the accelerated, next here, we have 35 racks, 1K nodes, and also we will have the 2 Sapphire Rapids processors and 4 NVIDIA Hopper GPUs, as I mentioned. Right? And what else? Yeah, the next generation, general purpose here, 7 racks accounting for 400 nodes of 2 NVIDIA Grace, with 240 gigabytes of LPDDR5. And on the accelerator, we'll have one rack of 24 nodes with 2 Intel Emerald Rapids and 4 Intel Rialto Bridge with 128 gigabytes. So this is what we will have, a lot of data here. Just to give you a glimpse of the internals of the general purpose compute node, basically, this is it. This is the 3 of them, the 3 different configurations that we'll have, like the regular ones with 256 gigabytes, the fat RAM modes with 1 terabyte, and also the hybrid memory modes with HBM and DRAM. So we'll have two nodes within the same, let's say, tray, dual node tray. There will be only one cable. It's a dual port going out from here also to save a little bit. And there's some water power dissipation. It's not water immersion. It's water here on the processors. So what I would like to highlight here from this next slide is the power consumption that we took care of course, because we're all constrained about the energy consumption of our facilities. So we accounted for the energy consumption in HPL runs for the different types of nodes. It varies slightly, but noticeably from 10.4 kilowatts for the HBM nodes to 12 kilowatts for the 1 terabyte of RAM nodes, and slightly less for the regular nodes. So the most power efficient or the less power hungry ones are the HBM ones. And liquid cooled power supplies as well. That's cool to have, right? So what else? Yeah, on the accelerator compute node, as I mentioned, there's 2 Sapphire Rapids and 4 GPUs. So basically, this is how they are wired and laid out. So there's some water cooling here, as you see. What I cannot tell as of now is whether this is water immersion or just water cooling in the dissipators, as we saw earlier. That I cannot tell, but from this diagram, it would look like there's liquid immersion. So, general purpose here. This 408 compute nodes that I mentioned with Grace processors and air-cooled chassis in this situation, we will have some immersion cooling pods. We're actually working with trying to get that. It's not easy. So, and the accelerated part with 24 compute nodes on Emerald Rapids and Intel Rialto, as you can see here. So these are some cool pictures. So if you have ever been before to BSC facilities, this is the chapel building. So it used to be a real church. There used to even to live nuns there. For many, many years already, it's not a holy place anymore. But just one of the facilities within campus. This is actually, you can see here the rest of the UPC campus. By the way, BSC is next to UPC campus, but it's a separate entity. And this is the new building. This is our new headquarters. Actually, we are told not to call it the new building anymore. It's the BSC Repsol building. We're actually growing as much as that we do not fit there anymore. It was planned a while ago, and then we do not fit anymore. By the way, we're hiring, of course, like everyone else. So yeah, what I was going to say here. So beautiful Mare Nostrum 4 or Mare Nostrum 1 to 4 site is here inside this chapel. You see here a bridge. This is a real bridge, walkable, where we walk usually. Many offices are there, including mine, so we come here to talk to the operations, to pick up material for visits to the Mare Nostrum, everything. So the Mare Nostrum 5 site and the new site is in there in the basement. I'll show more pictures. We expect to have always some part of our machines running in this part in the chapel, but we had to get a much larger space to host newer, larger computers. So Good news is that the beautiful chapel site will still be in use despite, and will have much more space next to it and actually connected over links. So this is a view, a transversal view of the facility of the new building, of the BSc Repsol WIT building, the headquarters, and all of the different spaces that we are using to support this Mare Nostrum5 running from the rooftop, where we have those cooling towers that move water on this pipe vertically, and here is the main site hosting the machine, but also side rooms that we need for different things, for power conversion, for the liquid pumps and all the stuff. So in total, it's about 3,000 square meters that we're using, with the main compute room being 847 square meters. It says 900 here, but I think it accounts for a little bit more than specifically just the compute room, which is over here. So this is as it was very recently, with only these towers here, but I'll show a lot more now. So if you are soccer fans, you may realize that this has actually the colors. Pete, we don't see it here as well as I'm seeing it on my screen, but it's red and blue, like Barcelona. It was a nice coincidence, but it was not by our choice. It's just how regulations have to be. So I believe red means hot and blue means cool. But it's a nice coincidence with the Barcelona soccer team. By the way, I'm not a soccer fan anyway, but for those of you who are, and for many people at BSc who are soccer fans, this is a nice coincidence. So there's also this fire detection and extinction via water mist, and air cooling. These are the air cooling towers that I showed earlier. What else? Oh, yeah, here you can also visit where the pumps are. I think they come next. The power distribution, right? The transformers. What else? The low voltage switchboard. The UPS. I think we do not have currently a UPS for Mare Nostrum 4, or we have never had it. For previous Mare Nostrums, we will have now a 10-minute duration UPS, which is nice to have. Anyway, our philosophy, or at least what I was told to when I was hosting visits to tell people who were visiting, is this is not a data center, so if there's an outage, people just have to relaunch their experiments, and whatever is in the main storage is not. You're supposed to have a backup somewhere else. But now, nicely, we will have a 10-minute UPS anyway, provided by Huawei. I think it was just the company or the one who made the requirements on the tender. So this is a picture of the rooftop before anything was installed. I was visiting, the group leads had the chance, we had the chance to visit it, so it was really cool, and now we see it full of cooling towers. It's impressive, the change that we see. These are the heat exchangers that you see somewhere else in the building. Interesting here, perhaps, is the degrees that we work with. So to the tower, 28 to 38 degrees, and to rack 30 to 40 degrees. And this is the total dissipation power of 13,500 kilowatts. Chillers here, as you see, there's again this temperature range of 30 to 40 degrees to rack, and the pumps that you can also see there, okay, with nice colors. Okay, so I hope you enjoyed the pictures. Now, USB supercomputers, we have quite a few of them already. We're working on the Mare Nostrum5 at BSc, and Portugal is working with Decaolion from Mac. And how what's the access, the planned access to this Mare Nostrum5? So 50% belongs to the USPC joint undertaking partners, so the infrastructure, and 50% belongs to the participating states. So out of that 50% belonging to the USPC JU, basically any organization belonging from the countries which belong to the USPCJU can request access via the multiple open calls. It's also open to industrial enterprises and SMEs, so it's nice to have. So different calls will have different conditions to gain access, right? Like, for example, you have multiple access nodes as of now. And the rest of it, the other 50% belongs to Spain, Portugal, and Turkey, proportionally to the amount of money they contributed, and they have their own, each country has their own rules for access. For example, in Spain, we reserve part of it to the Spanish supercomputing network, and some other part of it belongs to BSC, just for the management and the effort of hosting. It's not that much, a little bit, but we live happily with that. And this is all I had for Mare Nostrum. I guess so I will switch to a different slide deck and different mode of presentation, so if there's any question here, and I can take it, I'm happy to. Is that a recent announcement? Because these slides are very... okay, then maybe the slides are not... are before the... Yeah, the slides may be from before. Sorry, I was not aware of that. Then... well, I am not surprised about that. But anyway, yeah, sorry, this is the latest information I have. I didn't know myself. Thank you for letting me know. As far as I know, for the most immediate, there's no noticeable delays. For those which are farther away, we'll see. So, cross fingers. As of now, we do not expect great delays from plant. And as far as I know, there were penalties for delays for the providers in the procurement. So, I guess they will do their best. As of now, there's no big delays planned. Yeah, okay. So we're working with NVIDIA, with Gilad and his team, on offloading efforts, on making OpenMP be able to address the capabilities of DPUs. Let me just explain with the slides. So I'll start with short DPU refresher from our viewpoint. I know you've been hearing about the DPUs and blue fields, but let me just quickly express our viewpoint here. I'll review quickly the Doka APIs, the OpenMP target offloading, and then I will go into our efforts towards enabling OpenMP target offloading for DPUs, the upcoming MPI integration, and also some example, just toy example on how to use this. So, just a short DPU refresher. So, high-speed NIC or HCA or whatever the vendors want to call it, just now 400 gigabits and upcoming, as we have seen. Smart NIC, you can offload different parts of your workloads, like security or I/O. But with a DPU, you get this data processing unit, which is actually we call it's a very generic name. You have DPUs also in processing in memory, right? Here you have this general purpose processing cores that you can address. This is the part that we are talking about in this talk. You have a nice picture of an NVIDIA Bluefield DPU. Actually, in my view, it's really elegant, isn't it? And very clean design. So I heard from someone that Doka is for DPUs as what CUDA is for GPUs, right? I'm not mistaken, right? I can say that, yeah. So this is the API, the low-level API that we have to code to address these DPUs. And of course, or at least in my field, we try to abstract as much as possible from applications. We do not expect domain developers to engage into these kind of low-level APIs, which are pretty much computer science geeks like us trying to squeeze the most of the underlying hardware. So the Doka is fairly wide already, has a lot of APIs. We actually focus in this one, in the communication channel, which enables us to talk to the DPU via I guess the PCI Express, DMAs, and everything with some level of abstraction, which is nice enough for us to start communicating with the DPUs and offloading and asking the DPUs to do stuff for us. So, regular OpenMP target offloading, as we know it. So, just we have this Pragma OpenMP target. It does the compilation, the embedded for us, and does the data transfers, and then the execution transfers back and forth. It's really nice abstraction, and we have seen this morning a talk discussing a lot about that, and the trade-offs versus lower level APIs, OpenMP versus OpenACC. But we believe this is really cool for domain developers who do not want to engage into lower level APIs, and it's actually widely used. So how do we choose the device? We just give it an ID. This is probably a weak part of the OpenMP design from my point of view, but I will not get into that today. Because it's outside the programming model, we have to figure out which are the numbers of our available devices. So in this case, device 4 is this GPU, and we instructed here that we want to offload this part of the OpenMP to GPU, to device number 4, which is this GPU that we checked offline. Okay. So what's our intent for DPUs? And actually, I will refrain from saying it's working, but we're just debugging the last communication details. So most of the code is there. It starts to work. We just have some communications issues with the DPU that we are debugging with NVIDIA, and we're sure we will be solving them very soon. So actually, this is what we are developing, this support. So we are able already to embed this code in a fat binary that will execute in the ARM cores of the devices. So we just compile as we are doing right now with GPUs. And it's embedding the GPU binary into the host code. Here it works the same. We're embedding the ARM binary into the host code from our extended Clang. We have developed this new target library backend to address the blue fields. And this is using, as I said, the communication channel from Doka. And we have developed also a new Doka service for OpenMP that will run on the DPU and is able to communicate with this library. So we have this working, the target plugin, the cross compilation. We're just debugging the last communication issues here, but for a large part of it, it's already working. And this is actually a workflow of how it works. So we have this offloaded wrapper function, then it automatically sends the input data to the DPU through the communication channel API of Doka. The DPU receives the data. So we read this offloaded dynamic library, which is basically the ARM binary to be executed by the DPU. We send it to the DPU. It executes it and sends the data back. This is just a basic workflow, same as we would have in a GPU. It's basically starting to work for the DPUs as well. So how do we choose a DPU? How do we use this OpenMP target device for DPUs? Simply just select an ID, which is exposed now as a DPU and not a GPU. And actually, this is compatible with having some devices on the GPUs and some devices on the DPUs. It will work all together, and we're starting to look into experimenting with that. But out of the box, actually, it will work. So we are basically developing a transparent replacement for GPU offloading using exactly the same syntax for DPU offloading. So we're looking forward already. We're almost done with this part. We're actually looking for beta testers if you're interested. We really expect this to start working for beta testing in the next coming days, I would say weeks. Well, it was too optimistic, I guess, but we're really almost there. So we're looking forward to the next, we're already brainstorming and starting to implement toy codes. The main difference from a GPU and a DPU seen as a local accelerator is that the DPU has actually communication capability, so it can communicate directly. So we want to do MPI integration. As of now, what you can do is this. You get different ranks in different, so you see DPUs as one more node connected to the network, and then just they get rank numbers. So we want to abstract that. You can now, so there are quite a few papers already exploring this opportunity, successful papers, I would say. So you can just do intercommunicators with connect accept, or do NPM, the multiple program, multiple data with this MPI run syntax. So you just basically get different rank numbers and you work with them. The problem here, even though this is fully functional, it's a little bit of hassle to application developers who have to take into account that they have some nodes which are way weaker than the other ones, which are SPC nodes. So this has, compared to an SPC node, a few small ARM cores. So you have to kind of design your application for that with the MPI, which is not that appealing from a developer's point of view, from programmability point of view. So this is what we want to achieve, and we have already started working towards that with NVIDIA. So basically, we want to have just different ranks for different sets of hosts plus accelerators, as we have with GPUs. Actually, we could draw GPUs here as well. So there will only be one rank number for the different set of hosts, compute nodes. And we will be able to communicate any to any. So DPUs will be able to communicate with DPUs or with hosts and everything. So we can do this automatically. We just are looking forward to start making our tests and see how this works performance-wise. But basically, here, when you do OMP target device DPU, you can do computations, as I showed earlier, and as we can do with GPUs, but also you will be able to do MPIs. So if you are the receiver, you can do an offloading, then you can do no offloading, then it will be like this one, DPU sending to host, or you can also offload the matching receive. So maybe you can exploit this path. So all of this is upcoming. We already started working into this, and just where this is coming just farther away from the other support, which is becoming immediate. So just some example of how we envision this Halo Exchange. You all know how Halo Exchange works, right? We just have these halos that are the outermost part of the domain of our neighbors, and we need to exchange them every iteration, right? So this is what we could have. For example, we could have the innermost part accelerated on a GPU, and then the outermost part computed on the DPU and doing the data exchanges. Like seeing the DPU as an accelerator next to a network, which is basically what it is, local accelerator next to a network. This is the view that we want to expose to users. And basically, this is all about it. It's how we expose it programmatically. What's the semantics that we expose for this? Because right now, as of now, they are fully functional with just other ways of programming. We want to expose and explore exposing this way of working. Right? So basically, this we could potentially do this. We have already some code doing this, and just waiting therefore to hit launch whenever everything starts working. Right? So, okay, I'm right in time. So basically, this is like a little bit of code. You would offload where it is target, offload the inner part to a DPU. And this target with device 1, you offload the compute outer to the DPU, where you just compute the outermost part and do the receives and the sends directly on the offloaded code on the DPU. And this is where the main difference from GPUs will strive, conceptually, apart from the different nature of the architecture of the processors, which will make it interesting to decide where we compute everything, right? So just to finish and leave a few minutes for questions, if any, my final remarks. So there have been already very interesting use cases reported for DPU acceleration, like deep learning, MPI collectives, and even MiniMD, for example. So even Bluefield 3 upcoming will open the door to a lot more use cases because it will embed more powerful processors on it. So we are aiming at democratizing the easy use of local DPU acceleration for general purpose, right? So of course you can leverage these libraries, you can leverage MPI offloaded, but you can also give it a try with this. So stay tuned, this is coming very soon. We're already looking for beta testers. This is all starting to work. We are going to release it open source. And I think this is us. This is my team working on this. And with this, if you have any questions.